Welcome to UV Physics. So here we are discussing a new approach to solve any quantum circuit. That means we can find the output state by using this decimal notation method. So in the first lecture, I have already explained the method. So once again, let me explain briefly about this decimal notation method. For example, if I have a single qubit, let us say Q0, then I'm taking this as a 1. That means whenever that a qubit is on, that value is 1. I have taken like that. And if I have 2 qubits or 3 qubits or 4 qubits, any number of qubits you can take, then it is 1, 2, 1, 2, 4, 1, 2, 4, 8. The decimal values. If you want, you can write it as a ket notation also. It's not a problem, right? Okay. So next thing, for example, you have single qubit gate. Just I'm explaining briefly. So if you want more clearly, I request you please watch the first lecture. So single qubit is there. Let us suppose you have single qubit state and gate is also single qubit gate is there. Let us say U. So for this, what I have explained, the operations. The operation here it is U of. So there is no control, only target. Whatever you have, that is the target. Okay, 0 comma t. That's it. That U may be X, S, T, any single qubit you can take. Okay. So for example, in this case, we have only one. Okay. So that's why the operation is given by U of 0 comma 1. Now, for example, you have 2 qubits, that is 1 and 2, but you have a single gate here itself. Then how to proceed, how to get this operations? The operations here I have already explained everything. Operations, this is U of, first U is on this second state, that's why you have to take a 0 comma 2. After that you have to add whatever the remaining. It's a simple decimal addition only, no binary addition. It's very easy. So 1 comma 3, that's it. That means it will operate, it will make the changes or superposition or flip only these states only, 0 and 2 combination and 1 and 3 combination. 0 and 3 combination you won't get in this case. Okay, 1 and 2 combination also you won't get. That's the point. Okay, and one more example I will take. So for example, if you have 1 and 2, and here we have Hadamard gate. I'm just taking an example to understand, and here I have S gate. So whenever you are having like this, you can come from top to bottom. Single qubit gates, you can go from top to bottom or bottom to top. It's not a problem. But whenever you are making the tensor product, you have to always come from top to bottom. But remember, operations we are doing, not matrix multiplications. So that's why operations are from left to right, because the left side operator will operate on the initial state. We are trying to find the final state. Okay, so here the operations, you can take H first, no issue. H of 0 comma 2, and you have to add this one, that is a H of I will write like this to understand more clearly. So this is a H of 1 comma 3, and next you can take S, this is on 1, that's why 0 comma 1, and here we have to add the remaining 2, that is S of 2 comma 3, like this. If you have 3 qubits, then also I already explained this method. I request you please go through this. Definitely you will enjoy while you are solving this quantum circuits. It's very easy. I feel it's very easy. That's why I want to share with you. So please go through that method. And 2 qubit gates also I explained. Let me give that example also. 2 qubit gates. So for example, here we have 2 qubits and I'm taking control U. Okay, so this is unitary U and this one control U. This is a C and this is target. Okay, now you know if C is 1, then only this operator U will operate on T, otherwise no change. Output is a CT as usual, tensor product of C and T. But whenever C is 1, then only C and U operates on T. This is what we have discussed, generally. So initial state C, T become C ut only when this is C equal to 1. If C equal to 1, if C equal to 0, there is no change at all. Okay, everybody know this. But in our method, how we are doing this, so no need to write C, just take operations. So this is our method, a decimal notation method, operations. How to write? Once again, I am taking this 2 qubits, 1 and 2. It's easy, please follow 1 and 2. And let us suppose this is C and this is T. And here I am defining the operation as U of, earlier control is not there, that's why we have written 0 comma T. Now control bit is there, that's why you are coming from which bit? Control. So this is the starting, that a dot is the starting. C comma, you are coming towards T, just I am assuming like this, okay? C plus T, easy. In this example, U of, you are coming from 2 comma 2 plus 1 3. That means what? What is that U of 2 comma 3? That unitary operator will affect only those two states 2 and 3. It won't affect the other states 0 and 1. I hope you understand. For example, if you take, instead of U, you have taken a Hadamard gate, it will create a superposition of 2 and 3 only. It won't create any superposition of 0 and 1. If you take U as X, it will flip 2 and 3, 2 2 3, 3 2 1. 0 and 1 states remains the same. This is what I'm saying. Okay, so I have already explained all these examples. Maybe you will get one doubt. So for example, I have 3 qubits. Okay, so here only I have this control U operation. Then how to do this? Yeah, very simple. 3 qubits, notation 1 2 4. Then how to write the operations? Let us see. Okay, so initially where is this CU gate? Here we have. Okay, here we have. So please go there. So this is U of starting 2 ending 1, that's why 2 plus 1 3. For this you have to add the remaining one 4, that is U of 6 comma 7. Okay, now last one more example I will explain. And if you have 4 qubit states, but somewhere here I have this control U operation, then how to do this? Generally it is a tensor product of I, tensor Cu, tensor I. So here we have 1 2 4 8. Okay, so you need not to bother about that 1 and 8. Okay, you just operate this only, and after that simple addition only, but decimal addition only. Okay, so this is quite interesting. U of 4 comma 6, because of 4 plus 2 6. After that add the next state. You can add either 8 remaining or 1, but I am taking a least one first, plus 1. Then it is U of 5 comma 7, and this is important. Whatever the remaining state, decimal state we have, you have to add that 8 to the earlier all states. You have to add to that earlier all earlier states. That means after adding after adding 8, this become U of 12 comma 14, and this is U of 13 comma 15. Oh, that's it. So these 4 operations only will happen if this is a single. If a combination of gates are there, that also I have explained in the earlier classes, the first lecture and second lecture, so kindly watch. And today in this third lecture we are going to discuss about equivalent circuits. So let us start this third part, that is equivalent circuits. So here how to, that means we are going to discuss about two quantum circuits which are equivalent, that means which will give you the same output. Let us discuss. So here we have two qubits, okay, and this is only Z gate single qubit, and here we have a CNOT, and here I am taking the another one, so two qubits and CNOT gate here, but this time that is here and here also. Let us see whether these are equivalent or not. Okay, so proceed with our method. So decimal notation 1 and 2, here also 1 and 2, and you have to write the operations. So left to right, don't forget left to right. First I have z here, z of 0 comma 1, then I have to add 2, it's clear. Next x 2 to 3, that means 2 to 2 plus 1, you are coming from 2 to 1, that's why 2 comma 2 plus 1 3, that's it. And here also I am taking x 2 comma 3, and after that any z you can take, either upper one or bottom one, anything you can take. So z of 0 comma 2, I'm adding 1, and after that second z I am taking z of 0 comma 1, adding 2. Now see, I'm taking all the states at a time, that means initial state, this is the initial state. Okay, so here first z is operating on that, and you know already this first one is off, second one is on. Okay, I hope that also you know, right? So where is the 0? 0 is in off. Whenever you take a Z matrix 1 0 0 minus 1, this also I have explained already, I request you please go through that. Just divide into two columns, and this is the off, this is on. First column you have to take for off, and the second column you have to take for on. So that's why 0 is in the off state, that's why again 0 only. 1 is in on, that's why minus 1. 2 off, same. 3 on, minus 3, phase change. And after that again one more x is there, this one. Only it flip 2 to 3, 0 as it is, minus 1 as it is, it become 3 and it become minus 2. So this is your final state. Now let me check whether you are getting the same answer for this or not. So here again I am taking a 0, 1, 2, 3 initial state. Now first here we have x operation. So that is it flip only 2 and 3. So 3, 2. And after that z operation. Okay. So 0 off, 1 off, 3 on, that is minus 3, sorry, minus 3, and 2 is also on, minus 2. Next again z, 0 off, 1 on, and minus 3 on, that's why one more minus, that is 3. 2 is off, that's why same. Now if you observe carefully, here we have this final state, and these two final states are same. So that's why we can conclude that these two quantum circuits are equivalent. Let us go to the next one. So here I have taken two qubits. Okay, so first one here we have CNOT, and after that Z, and here first Z operation and after that CNOT operation, just like a commutation relation. Okay, let us see. So order, because order is reversed, no? That's what. So here we have 1 and 2. So first operations x of 2 comma 3. I hope everybody understand why it is x of 2 comma 3, 2 comma 3. And after that z of 0 comma 2, and you have to add the remaining, that is 1 comma 3. And here same 1 comma 2, that means sorry 1 and 2, 0 z of 0 comma 2, add 1, that's it, and x 2 comma 3. Now let us take 0 1 2 3. This is the initial state. First x operation 0 1 3 2. Next z operation, these two are off, these two are on, that's why 0 1 as it is, minus 3 minus 2. Now let me check this a second one. So 0 1 2 3, this is the initial state, and here z operation, so off, 1 is off, 2 is on, 3 is on, minus 2 minus 3, and x, I'm using that on and off notations only. Okay, so next one 0 1, it flip 2 and 3, minus 3 minus 2. Now this is the final state, and this is the final state, and both are same. So that's why we can conclude that these two quantum circuits are equivalent. Actually, this is not only for Z, this is valid for any diagonal matrix. That means what I am saying is, a small note, this is true for, here we have two qubits. What I am saying is, this is the CNOT, and here U, this is equivalent to, this is U, and here CNOT. But remember, this U is a diagonal. Examples that U may be Z, S, T, that's it. Okay, so identity no need to check, because if you take identity, both are same circuits only. So this is valid for any diagonal operator or any diagonal matrix. For example, here we have Z, S, and T. Okay, we'll go to the next one. So here we have two gates are given. Let us check, sorry, two circuits are given. Let us check whether they are equivalent or not. And if you take this rz of theta, that is a rotation operator about z axis, which is e raised to minus I theta by 2, 0, 0, e raised to I theta by 2. Wait a minute. Just now we have discussed, this is a, no doubt this is a diagonal operator, diagonal matrix. If the operator is a diagonal, okay, I mean diagonal matrix, then these both are equivalent only. Just now we have discussed. Okay, no need to check. Or if you want to check, you can proceed with this method. Let me explain that method also. So here we have 1 and 2, 1 and 2. First we have x 2 comma 3. Next we have rz 0 comma 2, and we have to add 1 1 comma 3. Next here also, let me write initially rz of 0 comma 2, sorry, and this is x of 2 comma 3. Now here 0 1 2 3 I have taken this initial state, and x 0 1 3 2 and rz. So here 0 and 1 are in off, 2 and 3 are in on. Okay, so I told you already, since it is a diagonal, only a phase factor will come to that state won't be changed, and you won't get any superposition state also. If all elements are not equal to 0, then you will get the superposition state. If a diagonal matrix is there, only just a phase change, and uh, diagonal elements are 0 and off diagonal elements are non-zero, then you will get a flip, that is x and y. So I hope I already explained in the earlier lectures. Please go through that. Yeah, phase difference is a 0, e raised to minus I theta by 2, 0. I'm writing ket 0. 1, same, e raised to minus I theta by 2, 1. 3, e raised to I theta by 2, 3. And this is e raised to I theta by 2, 2. Okay, that's it. So let us check the answer for the second one. So initial state I am taking 0, 1, 2, 3. So this is the initial state, and here we have RJ. So 0 off, 2 on, 1 off, 3 on. So 0, e raised to minus, because the first column is for off, second column is for on. E raised to minus I theta by 2 0, and e raised to minus I theta by 2 1, and e raised to here theta by 2 2, and e raised to I theta by 2 3. Next after that x. So x will flip only 2 and 3, the first two terms as it is, and here e raised to I theta by 2, 2 is a flip to 3, and 3 to 2, that's it. And if you see these two final states are same, so that's why we can say that these two are equivalent. Okay, let us go to the next one. Now here I am taking fourth one, the in terms of Hadamard operations. So here H gate, and here also H gate, and this is the CNOT, and another circuit I'm reversing this CNOT, and after that this Hadamard gates also like this. Okay, this is also just like a commutation, that means A B. Of course here it is a tensor product of H and H. Okay, and okay, let us see 1 and 2. Let us apply our method. Okay, so first H I am taking operations 0 comma 2, and we have to add 1 comma 3, and the next H, second H is also there, H of 0 comma 1, H of 2 comma 3, and X of 2 comma 3. So close here and come to this 1 comma 2, 1 and 2. You can write initially like this, operations 1 comma 3, because it is 1 to 2, 1 comma 3. You can take any H, H01 and H23. After adding 2, H02, and I have to add 1 comma 3, right? See, I'm not doing any binary addition or something, just very easy, just a decimal notation and decimal addition only. So I hope you are following. If you are facing any trouble, please let me know. And here I told earlier, if I take this elements of that first elements of that bracket, it is very easy to write the next state. This is what I said, but here it is not like that. It's okay. Now I'm taking 0 1 2 3, all the things at a time I'm taking. Let us try. So here 0 is there, which is a linear combination of 0 and 2, that's why 0 plus 2. I'm not writing in normalization constant. Finally I will write, because 2 Hadamard's are there, maybe you will get 1 by root 4. Let us see. And 1 off state only, 1 plus 3, 2 on state, 0 minus 2, 3 on state, sorry, 1 minus 3, and again one more H. So 0 off, 0 plus 1, 2 off, 2 plus 3. I hope you understand. This 2 is a linear combination of 2 and 3. This 0 is a linear combination of 0 and 1. 1 on state, that's why 0 minus 1, 3 on, 2 minus 3, 0 off. Just observe carefully. Here 0 plus 2, here 0 minus 2, right in the middle, minus to the above 1. And here 1 plus 3, and here 1 minus 3. I hope you are observing what I am saying. Okay, here 1 plus 3, 1 minus 3. 1 plus 3 already you have written. So write 0 minus 1 in the middle, minus 2 minus 3 like this. And after that we have X. Still we are doing the first circuit only, 2 to 3. So that's why finally I can write 0 plus 1 plus 3 plus 2, 0 minus 1 plus 3 minus 2, 0 plus 1 minus 3 plus 2, 0 minus 1 minus 3 minus 2, and a normalization constant 4 terms are there, 1 over under root 4. Okay, next let us say this is the A, and this is a B. So this is A output. Now I am coming to B. 1, 2, 3, 4. So first initially X we have 1, 2, 3. Here 3, 2, 1, 4. The remaining are as it is. Next we have Hadamard operation. So 0 off, 1 on, 2 off, 3 on. 3, that is a 2 minus 3, 2, 2 plus 3, 1 on, 0 minus 1, and 4. Oh, 1 minute, 1 minute. What is this? I'm sorry. I'm sorry. 0, 1, 2, 3. I'm sorry. So X, that is a 0, 3, 2, 1. So now initially we have 0. Okay, so 0 off, 0 plus 1, 3 on, 2 minus 3, 2 off, 2 plus 3, 1 on, 0 minus 1. Okay, right. And after that one more Hadamard is there. So here 0 off, so 0 plus 2. Next 1 off, that's why 1 plus 3. Next 2 on, 0 minus 2, minus 3 on, 1 minus 3. I hope you understand. 2 off, here see, sorry, 2 on, see here, that is 0 minus 2. Just see that above and change the middle sign, plus 1 minus 3. Already you have written 0 plus 1, and here it is 0 minus 1. Take that above 1 and change the minus. Okay, so I think something, no, absolutely right, only that order of numbers change. Okay, so because here I have taken h of 0 to first, here I have taken h of 0 1, that's why order of numbers change, but same state only, if carefully observe. So for example, if you check the last one, so this one check, so both are same. So 0 plus 2 and minus 1 and minus 3. Okay, so this is the advantage of this method. Okay, it's very easy, and the normalization constant 1 over root 4. So these two are same. So these two circuits are equivalent, right? So now let us take a combination of CNOT gates, and here first one I am taking 3 qubits I have taken, and first CNOT and the second CNOT. Here I am taking again 3 qubits. This time this is CNOT, and here another C. Okay, let us check whether they are equivalent or not. 1, 2, 4, 1, 2, 4. So this is the first CNOT, x of 4 comma 5, and 2 remaining, that's why 6 comma 7. Just add, very easy. X of 4 comma 6, because it is coming to 4 to 2, 4 to 2, and this is x of next remaining is 1, 5 comma 7. And let me write for this also immediately. X of 4 comma 6, add 1, 5 comma 7, x of 4 comma 5, add 2, 6 comma 7. So it will change only 4, 5, 6, 7 only. There is no 0 and 1, 2, 3. Okay, so that means 0, 1, 2, 3, no change, because no operation is involving with that 0, 1, 2, 3. That's why no change. So we have to check only this 4, 5, 6, 7. This is very easy. Okay, now start with 4. Always go from left to right. The starting is 4. 4 become 5. Don't write. Just continue, because this is all are same gates only, same operations only. No need to write. Earlier, why we have written step by step? So once you are getting x, next you are getting h. That's why I have written. Now continue the operation. 4 to 5, 5 to 7. I hope you understand. One more time. 4 to 5, 5 to 7. That's why I have written 7. Next one. 5. 5 to 4, 4 to 6. 6, 6 to 7, 7 to 5. You please try. 7, 7 to 6, 6 to 4. That's it. This is a final state. Okay, this is initial and this is final. Let us check the second circuit. Again, I am taking 4, 5, 6, 7. Now you please try 4 to 6, 6 to 7. That's why it's a 7. Next 5, 5 to 7, 7 to 6, 6. Next to 6, 6 to 4, 4 to 5. 7, 7 to 5, 5 to 4, 4. The same. Okay, so that means here we have commutation relation. So these two are equivalent. So next here we have 3 qubits, but a CNOT gate, that is uh, here from 1 to 4, 4 to 1. So this is equivalent to what? So this is also quite interesting, and here we can draw an equivalent circuit like this. So take only one step. One step means 4 to 2. Take only one step, 4 to 2, and again 2 to 1. Just to break it. Okay, you came from 4 to 1. Just take it as a step. 4 to 2, 2 to 1. Repeat that again one more time. Repeat. That means 4 to 2, 2 to 1. And you can take a reverse one. Reverse one means just take a mirror image. Mirror image means you can take a, sorry, not mirror image, reverse order. Reverse order means right to left. So that means here first one, this one, observe carefully, this one I am writing, this is right to left. Next above, okay, I hope you are seeing, this is the third one which is below, and again the next one like this. Okay, so once you got this, you can reverse the order, not a mirror. Yeah, you think you can take it as a mirror image also. I think, for example, if I keep one mirror here, let us say this is a mirror. Now this way, this gate came here. Yes, absolutely. This one, and here this one, and next this, and next this. Yeah, correct only. So, but let us check by using our method whether this is right or wrong. Okay, so now I'm taking the first one, that is x 4 comma 5 adding to 6 comma 7. Next here combination is there, x 1 2 4 1 2 4, x 4 comma 6 add 1 5 comma 7. So many are there, that's why I'm taking a little bit this side. X 4 comma 6, x 5 comma 7, next x 2 comma 3, add 4, this is 6 comma 7, next again x 4 comma 6, and x 5 comma 7, and x 2 comma 3, and x 6 comma 7, same repeated. Okay, so let me write this also. So here third one I am writing, this is x of 2 comma 3, first one always left to right, 2 comma 3, 6 comma 7, so after adding this, take the next x gate, that is 4 comma 6 and 5 comma 7, and repeat again the same thing, 2 comma 3, let me write properly, and repeat the next one, right. Okay, so here we have only 4 5 6 7 combination only, it won't change any 0 1 2 3. Now you got a doubt here, That means first let me finish this first one. A, B and C. We have to show that all A, B, C are equal. So here 0, 1, 2, 3, no change. So 0, 1, 2, 3. And next 4, 5, 6, 7 and 4 to 5, 5 to 4, 6 to 7, 7 to 6. Next I am coming to this. Now observe carefully. So here 2, 3, 2, 3. Here in the middle we don't have 2 comma 3. That's why you can bring this side and x that is identity. So there is no change in 2, 3. That's good. Next, that's why here 0, 1, 2, 3 remains the same. I hope you understand this method. Next 4, 5, 6, 7. Now 4 to 6, just proceed from left to right. 4 to 6, we'll use this. 4 to 6, 6 to 7, 7 to 5, that's it, 5. Next 5. 5 to 7, 7 to 6, 6 to 4, that's it, 4. Next 6. 6 to 4, 4 to 6, 6 to 7. Till the end, please proceed. 7. 7 to 5, 5 to 7, 7 to 6. Same. Still not understanding? See the third one. So here also same. Here there is no 2 comma 3. So that's why I can bring together and I multiply x square 2 comma 3, that is identity 2 comma 3. So 0, 1, 2, 3, 0, 1, 2, 3, no change. Now I'm checking this of 4, 5, 6, 7, right? So 4. Start from left to right. Here there is no 4, then go to the next one. 4 to 6, 6 to 7, 7 to 5. Next 5. Here there is no 5, then go to the next. 5 to 7 and 7 to 6, 5 to 7, 7 to 6 and 6 to 4. Okay, so 4. Next 6. 6 to 7, see the second one, 7 to 5. Next there is no 5 in the third, go to 4, 5 to 7, 7. Next 7. 7 to 6, second one, 6 to 4. Next there is no 4, last one 4 to 6. That's it. So all are same only. So that's why all these quantum circuits are equivalent. Okay. So one more time, whenever you are having this CNOT gate, after jumping one qubit state, that means 4 to 1. Actually 4 to 1 came, in the middle there is a 2. So what I'm saying is one step, take only one step, and from there again take one more CNOT connection. So from 4 to 2, 2 to 1, and repeat the process 4 to 2, 2 to 1. You can take the same thing reverse also. Reverse means yeah, like this. You please check this one. So what I am saying is just take a 2 stages, 2 steps. Here 1, 2, 4, directly it is going from 1 to 4. So what I am saying is first go from, just go like this, 1 to 2 and again 2 to 4. Next repeat the same process, 1 to 2, 2 to 4. You can take the mirror image. If you place a mirror, okay, so here top, next bottom, next top one, next bottom. So I request you, please try this and check whether all these things are equal or not. Okay, and I think this, like this also we can proceed. Maybe for example, if you have 4 qubits and from top to bottom we have like this 1, 2, 4, 8. That means you have 8 to 1. Okay, so this one you please check, do it yourself. and if you are facing any trouble, please inform. Now here, if you have 4 qubits, that is 8 to 1, so you have to take only one step at a time. I think this, I didn't check, you please check. So 8 to 4, 1 to 4, 8, 8 to 4, and 4 to 1, and again 8 to 4, 4 to 1, and take the mirror image. So here, this one first, next top, next bottom, next top, like this. Okay, so I didn't verify this. I hope this may be correct again. And again, if you want, you can divide this also. Like this we can divide in the, but you have to repeat that step, whatever splitting you have taken, that is directly 8 to 1, but you break it 8 to 4, and after that 4 to 1. So you have to repeat that process one more time. Okay, so I hope this is what I observed. I hope you understand. Okay, so this is quite interesting one. So here we have CNOT gates and Ry of theta and Ry of minus theta. First let me write what is Ry of theta. So this is cos theta by 2 minus sin theta by 2 and sin theta by 2 cos theta by 2. And next, if I take Ry of minus theta, so cos theta by 2 only, and this becomes sin theta by 2, and here minus a sin theta by 2 and cos theta by 2. So that means what happened? The diagonal elements interchanged. This first diagonal and second diagonal are interchanged. Yes. Okay, right. Okay. Now let me apply our technique. So first one, x 2 comma 3 over, and this ry, just I am taking a minus there. Okay, theta I am not writing. So this is 0 comma 1, and add, that is 2 comma 3, and next again c0 2 comma 3, next again ry, this is a plus only. Okay, so I am not writing anything, otherwise you can write plus. So this is a 0 comma 1 and ry plus 2 comma 3. Now carefully observe. Now here, see, here we have 0 comma 1 and 0 comma 1. In the middle here we don't have any 0 comma 1 combination. That's why you can that means whenever if you observe this one, top one, so you can bring this ry plus this side, because there is no 0 comma 1. So that's why these two directly multiply and this become I of 0 comma 1. Oh, 0 comma 1 is not changing. So only here the change is between 2 comma 3 only. Okay, so this one is quite interesting. Here finally we have x 2 comma 3, x 2 comma 3, ry minus 2 comma 3, and x 2 comma 3. Carefully observe. And one more is there, ry plus 2 comma 3. Now this one, we have x, an operator, and x. So here I will tell you a small thing. For example, you have Pauli X matrix here, and this is A, B, C, D, any matrix, and again x here. And earlier, I think earlier lecture series, I have explained these techniques also. So this x will operate on this, that means rows will interchange, because a Pauli X matrix, if you interchange the rows, you will get identity. If you interchange the columns, you will get the identity. So that's why it will flip rows and columns. That means whenever it is multiplying any matrix, this is a small technique. And this is this side, that's why you can take column. Right side rows, and this side you just take it as a column. Okay, so now you have to interchange both the rows as well as both the columns. Then what will happen? Here D will come, here A will come, here B, and here C. You please check. So finally what I want to say is, whenever you have X and a matrix A, B, C, D and X, this is nothing but just interchange AD and BC. That means D, B, C and A. This is a small observation. So then here I'm X Ry minus X. Now go to Ry minus. Okay, earlier I said one point. Please observe carefully that Ry theta and Ry minus theta. If you interchange that diagonal elements, uh, first diagonal elements interchange and second diagonal elements interchange, then you will get the other one. So here Ry minus theta, just interchange. Cos theta will come here, cos theta will come here, no same, but minus sin theta will come here and sin theta will come here. So this will become cos theta by 2. Just I am writing again, here minus a sin theta by 2 and here sin theta by 2, and this is a cos theta by 2. Of course this is nothing but Ry of theta. So this is nothing but Ry of 2 comma 3. So finally we can write this entire thing is equal to Ry. Now I am not writing plus, it's okay, 2 comma 3, and again Ry of 2 comma 3, that means Ry square 2 comma 3. Okay, 2 times. So if you observe carefully, this entire circuit is equivalent to only 2 3. Only operation is 2 and 3. 0 1 remains same only. That means I can construct one control U operation which is like this, Ry square. See, uh, if you want to construct quantum circuit from this operation, this first one is a C and second one is a C plus D. So here we have 1 and 2. It's very clear, control bit is a 2 and it is coming to 1. That's why Ry square theta. That's it. Okay, so like this we can check by using this technique, and I hope you understand this also. So here what I have observed some interesting thing about this Rx theta, that means rotational operator about x-axis. So if you take this Rx of theta, this is cos theta by 2 minus I sin theta by 2 and minus I sin theta by 2 cos theta by 2. Just observe carefully. Just now I have explained that the diagonal elements, if you interchange that first diagonal elements, no change, and if you interchange that second diagonal elements, uh, no change. Okay, so that means x rx is x rx x equal to rx only. The reason is that is Pauli X matrix, and here this is the rotation about x-axis. That's why this behavior came. What I'm saying is, if you take x, rx and x, then what it will do, this will interchange the rows and this will interchange the columns, again you are getting rx. So this we can see like this also, x, rx, I am multiplying on x inverse on both sides, that is a rx, yeah, x inverse, no issue. Now this x inverse become I, so I can take this as a x, rx identity, and rx x inverse. X inverse is nothing but x only, because x into x square equal to identity, so that's why this is also x. Oh, I think this is a commutation relation exists. So that's why we are having this equivalent quantum circuit, here CNOT and here Rx of theta, and so this is a commutation x rx, here rx of theta and the c0 like this. So just observe x rx and rx x. And how to check? By using our technique. This is 1 2 1 2. Okay. So this is first one left to right, x of 2 comma 3, and after that rx of 0 comma 1 and rx of 2 comma 3. Next rx of 0 comma 1 and rx of 2 comma 3 and x 2 comma 3. So just now I have discussed already, this is rx of 0 1, this is also rx of 0 1, so no issue. And this is x rx and this is rx x. So x rx of 2 comma 3 is equivalent to commutation relation rx into x of 2 comma 3. So both are same, just now we have derived here. So that's why we can say both these two circuits are equivalent. So not only this, and the second one, that means if you take up reverse, so the reverse CNOT I have taken here, and this time Rx is here, because X Rx combination is equivalent to, so here it is Rx of theta, and after that reverse CNOT like this. If you want, you can check this one also. Okay, right? So finally this is because of the property x into rx is commutes, that means equal to rx into x. It's not surprising, this is rx means rotation about x axis. Now y ry equal to ryy, yes, z rz equal to rzz, obviously. Okay, right. The next one, let me take another interesting one. So here I am taking one circuit. This is C0 and Rx of theta and reverse C0. So taking one more. Oh, okay. So there, let us check. It's easy only. Just now we have discussed. Now if you carefully observe here, Rx, X. So you can interchange X, Rx. So the remaining is as it is. This is the C0, no change. This is the C0. Okay. So only we have applied this commutation, this one. Okay, here, and this gate is as usual change. Sorry, as usual same. So if you want to check, you can check by using our technique. Okay. So let us say 1 2. Let us say 1 2. So this is x 2 comma 3, rx 0 comma 2, rx 1 comma 3 and x 1 comma 3. This one x 2 comma 3 and again x 1 comma 3 and again rx 0 comma 2 and rx 1 comma 3, like this. So you know what is rx operator. So rx of theta already I have written here. So just to go through this and apply. So first column off, second column on. Okay, I hope you know that. And in this bracket, first one is off, second one is on. Okay, right. And the next one, this is also quite interesting. So for example, here I have a CNOT gate and another CNOT gate. So simply here I am writing Rx, theta I am not writing. Okay, and what I am doing is just reverse that two CNOTs. Then that Rx will come to the first, that means here. If you fill the two C0 gates, that Rx is coming down. So let us check whether these are equivalent or not by using our technique. This is 1 2 1 2. So this is x 2 3 and rx02, rx13 and x23, and this is x1 comma 3 and rx0 comma 1 and rx2 comma 3, and here it is x1 comma 3. Okay, now see, if you observe carefully, here we have right, see this one 2 2 3 this side and 2 2 3 x gate x but 2 comma 3 operations. So I told you already, so this side rows will interchange and this side columns will interchange. So finally wherever you have 2 in the row, that means matrix element 2 2 2 3 like that, 2 2 2 3 will become 3 3 3 2 rows, and column elements if you have 2 2 and 2 3 and 3 3 like that 3 2, so 2 and 3 will interchange. So that's why what I am saying a small technique. So here 2 become 3, 3 become 2. If you want you can check. This finally become rx of 0 comma 3 and rx of 1 comma 2. So this final operation is this one. That means it change only 0 3 combination and 1 and 2 combination. Okay, and similarly check here. So here we have 1 3 and this is also 1 3. So carefully observe, 1 is replaced with 3 and 3 is replaced with 2, because right side you have same operation and left side also you have same operation. So right side rows will interchange, left side columns will interchange. So final operation is rx 0 comma 0 comma 3 and rx, oh sorry, this is 3 comma 1, I'm sorry. So 1 become 3 and 3 become 1. So that is rx 2 comma 1. Now you got a doubt. So are they same? Yes. This rx 1 comma 2 and rx 2 comma 1 same. The reason is if you interchange that elements you will get the same thing. If you want you can check. So both are same only. Right. Okay. Now let us go to the next one. So the next they have given this circuit to show that both these two are equivalent. It's very simple. Here we have Rx gate, and please carefully observe this. And this is nothing but you just take a reverse CNOT and that Rx will come here. Already we have seen the same thing. The rest of the part is not changing anything. Okay, like that. And the next one, this is a very interesting one, last one. And for example, you have this 2 qubits, and this is a CNOT, and here we have Rx, and this is Rz, and here we have a CNOT again. They're asking to show that reverse CNOT, and Rz and Rx will reverse. That means here Rz will come and here Rx will come. First let us check whether this, how these two circuits are equivalent. Now this is 1 2 and this is a 1 2. So here we have x 2 comma 3. So take the operations rx 0 comma 2 and add 1 comma 3, and again one more rz is there, careful. So this is rz 0 comma 1 and add 2 comma 3 and x 2 comma 3, and after that this is x 1 comma 3, next rx 0 comma 1 and rx 2 comma 3, next rz, anything you can take, it's not a problem, rz 0 comma 2 and rz 1 comma 3, and the next x 1 comma 3. Right. So Now we have to check whether, so I'm leaving this as an exercise to you. So what you have to do is, you know what is Rx and what is Rz. First let me write this Rx. This is cos theta by 2 minus sin theta by 2 and minus sin theta by 2 cos theta by 2. So if it is off state, take the first column. If it is on, take the second column. Similarly, Rz also, I hope you remember. This is e raised to minus I theta by 2, 0, 0, e raised to I theta by 2. So off and on. So you please proceed just like this. I will do one step for you, 0, 1, 2, 3, and here x gate 0, 1, 3, 2, and after that Rx. So this 0 is off state, that's why cos theta by 2 0 minus I sin theta by 2 2, and the next 1 off state, cos theta by 2 1 combination, minus I sin theta by 2 3. Next 3 is in on, so that's why 3 is on. That's why we have to take the second column, minus I sin theta by 2 1 plus cos theta by 2 3, sorry. Next 2 on, that means the second column, minus I sin theta by 2 0 plus cos theta by 2 2. And after that Rz, first one I am doing, second one I request you please do. If you are not getting, please contact. Rz off and on, only phase change. Okay, so 0 phase change will be added, that is cos theta by 2 e raised to minus I theta by 2 0, like this. Okay, minus I sin theta by 2 and 2 is off, this by e raised to minus I theta by 2. You can write this side also, it's not a problem. So like this, please proceed yourself, and if you are not getting the answer, please contact. So these two are also equal, and by using this we can solve one a typical circuit like this. We have the CNOT and Rx, and again CNOT, Rx, and this is Rz, the CNOT. Okay, so they are asking to show that another circuit which is like this, CNOT, Rx, reverse CNOT, and Rz, and here Rx, and this is CNOT. Okay, so one second, I think this is yeah, oh sorry. So they're asking to show that this one, sorry, CNOT and reverse CNOT, Rx, and here Rz, and here Rx, and finally reverse C, like this. Okay, fine. Now just now we have discussed one technique, observe carefully. So this is nothing but reverse CNOT and reverse CNOT, that Rx and Rz also reverse, Rz and Rx. So by using this circuit is modified. Okay, so first CNOT as usual, next Rx is as usual. Now I am applying this, then it will become reverse CNOT, sorry, here Rz and here Rx and reverse CNOT. And after that, earlier we have already seen this commutation relation, observe carefully this one. So this can be written as Rx CNOT, CNOT Rx. Already we have verified this. Okay, so finally this become CNOT, and I'm applying this one, So this is a reverse CNOT, and Rx here, Rz here, and Rx as usual here, and reverse CNOT. So I hope you understand how I have applied this method. Okay, so what I observe is final observation. This is true not only for Rx and Rz. For example, you have this one what I observe. So here C0, here C0 is there. Let me take a little bit big one. So here a C0 gate, and here C0 gate, and here we have a single qubit where we are having A, B, B, A. Observe carefully, the diagonal elements are same and off diagonal elements are same, which is in case of Rx. And here any diagonal matrix, this must be a diagonal. That means let us say this is a C 0, 0, D. Then what I observe, I have verified this, and reverse C0, reverse C0, and those two operations are interchanging. Here you are getting the diagonal C0, 0D, and here you are getting that upper operation AB, BA. So earlier case, why it is happening, why it is correct, because see this one. Here Rx, if you interchange that first diagonal and interchange the second diagonal elements, you will get the same matrix again. And that means A, A, B, B, like that. And the next RZ, RZ is a diagonal matrix only. So that's why this is happening, right? And till now we have discussed an alternate method. By using alternate method, how to check the quantum circuits are equivalent or not, equal or not. Okay, so I hope you understand. If you have any trouble, and if you are facing any trouble in solving the circuit, so please contact. Okay, so thank you, and we will meet again in the next lecture.